Welcome to the Chapter 19 videocast of some sample problems for Chapter 19. It's recommended that you follow along with your packet of slideshow slides and the sample problems from Chapter 19 pages that start right here with the question that says, predict whether the following processes are spontaneous as described, spontaneous in the reverse direction, or in equilibrium. First question says, when a piece of metal is heated to 150 degrees and added to water at 40 degrees Celsius, the water gets hotter. Well, is this spontaneous, non-spontaneous, or spontaneous in the reverse direction, or is it at equilibrium? Well, we all know that when you put a hot thing in water, the heat from that thing, from the hot thing, goes to whatever the colder thing is. And in this case, the thing that's hot is a piece of metal, and the thing that's not hot is the water. And we know that that happens by itself. And so we say that that is a spontaneous, or it happens naturally, a spontaneous occurrence or a spontaneous process. Second question says, water at room temperature decomposes into, that's supposed to say into, H2 and O2 gas. Well, we don't spontaneously see hydrogen just exploding when you bring fire near where water is. And so we'd say that this is a non-spontaneous process, because to make hydrogen from water, you need to, of course, either drive some electricity into it or add some energy to it to break up into its component, hydrogen and oxygen. Letter C is benzene vapor at a pressure of 1 atmosphere condenses to liquid benzene at the normal boiling point. 80.1 degrees. Well, the definition of the normal boiling point is when the vapor is in equilibrium with its liquid. And at that point, then, when the vapor is in equilibrium with its liquid, it doesn't tend to spontaneously all go to vapor, and it doesn't tend to spontaneously all go to liquid. And so we say that the process there is at equilibrium. And it's neither spontaneous nor non-spontaneous. It's just at equilibrium. If a process is non-spontaneous, does that mean that it cannot occur under any circumstances? Well, no, that's not true. It can occur, but what's it going to take? Well, it's going to take some energy to make that process happen. It just means that it's not going to happen by itself, or it's not going to happen naturally. The next question gets into a little bit of the quantitative nature of entropy. And remember, entropy is symbolized by delta S. And we usually look at the entropy of the system. So we usually put a little SYS underneath there, although usually in testing situations like the AP exam, they don't put the SYS underneath there. And we'll ask questions as to what happens to the entropy of the system. Does it increase, decrease, or stay the same? Well, an equation to describe the entropy of the system is that the heat of the reversible process divided by the Kelvin temperature can tell us the entropy of the system, usually when it's at a point where it's going to have a phase change or a change in state. This question says, the element mercury, a silvery liquid, is at room temperature. The normal freezing point of mercury is negative 38.9, and its molar entropy of fusion is 2.29 kilojoules per mole. What is the entropy change of the system when 50 grams of it freezes at the normal freezing point? So we're told we're at the normal freezing point, and this means that we're at a point where we're going to change state. We're going to go from a liquid to a solid. And to be able to calculate the entropy of this system, what we need to know is the heat at this system. That's what Q stands for. And we need to divide that by the Kelvin temperature at that system. Well, we're told that the enthalpy of fusion, now the enthalpy or the heat of fusion, is simply the heat when something is changing phase. In this case, fusion means fusing from a liquid to a solid. And we're told that that's 2.29 kilojoules per mole of the substance. Well, we don't have a mole of the substance. we have 50 grams. And incidentally, this is also called the molar heat of fusion. And I don't know if you remember when we talked about things that are molar, it always means per mole. So it's the amount of energy per mole. So they might trick you sometime by just saying it's the molar heat rather than the molar enthalpy. It just means the same thing, just another way of saying it. Well, we don't have a mole, we have 50 grams of it. And so what we need to do is take our 50 grams of mercury that we have and convert that to moles. There are 200.6 grams in 1 mole of mercury. And we know that for every 1 mole of mercury, it's going to take 2.29 kilojoules to change that phase. In this case, we're going to freeze it. And so we're going to remove energy from the system. Remember, the system is our mercury atoms. And so we'll say that it is a negative 2.29 kilojoules because we're losing that energy. Well, if we multiply these together and do our division by 200.6, we end up with a negative 0.571 kilojoules. Entropy for a system is usually given in joules per Kelvin, not kilojoules per Kelvin. So we need to change this from kilojoules to joules. And remember that there are 1,000 joules in a kilojoule. So we multiply it by 1,000 and it turns out to be negative 571 joules to freeze this system. Now we can take this and put it into our equation for finding the entropy, and the entropy of the system will be equal to negative 571 joules. Remember, entropy is usually given in joules, and enthalpy, remember delta H or Q, is usually given in kilojoules. That'll become important later on in the chapter, so you don't get confused between joules and kilojoules for those two sets of units. Then we need to divide it by the Kelvin temperature, and the temperature is negative 38.9 Celsius. And remember, you have to add 273 to that to make it be a Kelvin temperature. So when I take negative 38.9 and add it to 273, I end up with 234.3. If I take and divide those two numbers, I end up with a negative 2.44 joules per Kelvin for my entropy. Here's a second question that's very similar. It's called the extra problem. This problem is on page 809 in the 10th edition of Brown-LeMay Chemistry, and you're more than welcome to take a look at that and try that one on your own just to see if you've got this process that we did up above here kind of down in your mind. At the bottom of the page, there's a couple more thought questions. The first one says, the second law of thermodynamics says that entropy, and I like to think of it in terms of entropy as like the rearrangement or the disorganization of the system. And the second law of thermodynamics says that the world is becoming more disorganized. And so entropy is always increasing. And things that are spontaneous favor that, or I should say it the other way around. Things that become more disordered generally are spontaneous. And we'll look more tomorrow at what causes those things to be spontaneous mathematically. Well, in the mid-1800s, late 1800s actually, a gentleman named Ludwig von Boltzmann actually gave some conceptual meaning to entropy. And he talked about entropy in terms of things called microstates. And this is talked about mostly on page 813 or so in your textbook. And he said that all molecules have several different ways of moving. There's translational, vibrational, and rotational motion for all molecules or all atoms, all molecules. And when this happens, we can take a snapshot of the positions and speeds and vibrations of all these molecules. At this point, if we have a mole of things, we have a particular set of 6.02 times 10 to the 23rd positions and energies for individual molecules. We call that a microstate for that particular system. Well, we can use the tools of statistics and probability to determine the total number of possible microstates. And each thermodynamic state has a characteristic number of microstates associated with it. And we use the symbol W to mean this possible number of microstates for a particular sample. And this really simple equation that Ludwig von Boltzmann developed actually describes entropy. K is called the Boltzmann Constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin, and that's on page 813 in your text. If you want to see a beautiful picture of Ludwig, here's his gravestone right here. And you can see that they've actually got his equation up here. S equals K log W. Back in those days, log meant natural log as well. And so we have the natural log equation written right here on our sheet. So if you want to know more about that, take a look on page 813, and sometimes understanding that there's all these different statistical ways of describing how things can be arranged allows us to understand what entropy actually is a little bit better. If you'll turn the page, there's a few more conceptual questions about predicting what the entropy of a system is. This says, predict whether delta S is positive or negative for each of the following processes, assuming each occurs at a constant temperature. I'm going to zoom in on these equations a little bit more so we can see the states of matter a little bit better. And if you take a look at letter A, notice that we're going from a liquid H2O to a gaseous H2O. And when you do this, what's going to happen to the entropy of the system, the delta S? Is it going to become more disorganized? Is it going to have more microstate possibilities? Or is it going to have less? Well, as you know, gases are obviously arranged further apart than liquids. And so since we're going from a liquid to a gas, the entropy, we say, would increase. The entropy would increase. There'll be an increase in delta S for this process. And so the sign for this would be positive. It would be a positive delta S for this process. Let's look at the second one now. This is silver ions and chloride ions becoming silver chloride solid. And in this process, the ions, which are free to move throughout the volume of the solution, form a solid in which they're confined to a smaller volume and are restricted to more highly constrained positions. Therefore, we've actually organized it a little bit more, and there's less microstates for it to move around in. And so we say that this is a decrease in entropy, and so we'd say that delta S would have a negative value in this case, a negative value. Letter C, you can see that we have solid iron and gaseous oxygen, and it's going to make a solid Fe2O3. Well, the particles of the solid are confined to specific locations and have fewer ways to move than do molecules of a gas. Because O2 gas is converted in part to the solid product Fe2O3, we say that the delta S has become negative, and therefore there's a decrease in the microstates of the system. Lastly, we have N2 gas and O2 gas going to NO gas. And if you look at this just from a gaseous standpoint, we have 1 mole of gas here, 1 mole of gas here, and 2 moles of gas here. So 2 moles on this side and 2 moles on this side. So the entropy change is going to have to be small because we have the same number of moles of gas on both sides. The sign of delta S is impossible to predict based on our discussion thus far, but we can predict that delta S will be fairly close to 0 in this case. There won't be a whole lot of change because we're going from 2 moles of gas to 2 moles of gas on this side of the equation. A good one to discuss. Let's look down at this next sample problem. Here it says, choose the sample of matter that has the greater entropy in each pair and explain your choice. Well, in the first one, we have NaCl solid and we have HCl gas. Both of them have 1 mole and both of them are at 25 degrees Celsius. Well, we'll notice that one's a solid and one's a gas. We'd think that the one that is a gas is more free to move about and therefore could have more microstates or more places to arrange itself. And so it would have the greater entropy. greater, more possibility of arrangements, and therefore the greater disorganization. In this second one, you can see that we have 2 moles of HCl gas or 1 mole of HCl gas at 25 degrees Celsius. Well, we'd say that HCl here has twice as much, and so it has twice as many possible microstates. So the 2 moles of HCl would definitely have a greater entropy, or a greater way to organize it, be disorganized if it wants to be. Lastly, we have 1 mole of HCl gas and 1 mole of argon gas. Well, notice they're both 1 moles of gas, so there's probably not going to be a lot of difference there, and they're both at the same temperature. But it turns out that the HCl molecules versus the argon atoms, remember HCl has 2 different kinds of atoms in it, and argon doesn't. The HCl has a higher entropy because the molecule is capable of storing energy in more ways than argon because of the bond between the hydrogen and oxygen. So we'd say HCl would have the greater entropy. Okay, last question. If you're told that the entropy of a certain system is 0, what do you know about the system? Well, if you take a look on page 818 of your text, it talks about the third law of thermodynamics. And this question actually addresses that question, that third law. And it says that the entropy of a pure crystalline substance at absolute 0 is 0. And so if you have something that has an entropy of 0, that means it has no ways of rearranging itself or having any other statistical organizations. And so we'd say that this substance would be at absolute 0. If you know the entropy of something is 0, you know it's at absolute 0.